Alright there, pop stars, let's get popping on this problem. So the whole point of this video is to kind of bring to light maybe some of the geometry involved in this problem, some of the algebra involved in this problem, and kind of bring them together to hopefully give you a more complete understanding than what the 40-something minutes in class could have provided, because frankly this problem is very, very complex, as some of you guys have found out the more you have tried these. So this is just one example. I believe it's number 4, but all the problems are worked in a similar kind of style. So there's two distinct parts to this problem. One is the geometric idea that tells you where to position your points, and then there's the algebraic ability to carry that out to actually find the distance. So geometrically, the idea is not huge. I'm asking you to find the distance between these two lines, but notice I'm asking you to find the distance, not just any distance, which means the distance I'm looking for has to be carefully arranged and completely unique. And certain distances that you guys were trying in class simply don't do that. For example, as a non-example, emphasis on the word non, meaning it doesn't work, some people tried to show me this distance. They're saying, hey, why don't you just take the distance here that occurs between the two intercepts? Okay, so it does meet the criteria of being purposely placed on this diagram, but it does not meet the criteria of being completely unique. What I mean by that is that I can totally find another distance between these two lines in a different orientation, meaning that if I take this point, boom, rotate it, pendular style up here, I now have the same exact distance occurring on the other side of the lines. I know I went off the grid and that was kind of hard to understand, but let me use this example a different way. Another bad example people gave me was this distance. What do we find the x-intercept distance? Hey, again, they're going to be carefully placed, but it's not going to be unique. Meaning, if I look at the distance here, lock this point, and then swing this, look what happens. I'm not trying to change the distance, and you can kind of get a sense of what I'm doing. That distance occurs at two different places using a different orientation on this grid. It's more exaggerated if I bring it out even farther. So like this distance occurs twice. So although this is uniquely placed, it is not, is purposely placed, it is not unique to this grid. What we need is a distance that defines how far apart these lines are that only occurs once. So not one that can be reproduced, not one that can be duplicated, one that is completely unique to this problem and these lines. To do that, all we have to realize is that we have to orient them perpendicularly, meaning that this line that defines two different points, one in each line, is oriented in such a way that it forms a right angle with both lines. Now this is brilliant, and let me kind of tell you why. I can't do that kind of like multiple placements for the same distance kind of idea we just explored. If I try to move this left, I try to move this right, I actually come off the line and it's not even a usable distance. The only time it's ever going to measure distance is a time and moment when it's perfectly perpendicular. And that's the geometric idea behind this. The shortest possible distance between any two lines is defined to be a perpendicular distance between those lines. Man, that sounds like something you should write down. Yep, that sounds like something you should write down. So I'll say it again. The shortest distance between any two lines is parallel lines is defined to be on a perpendicular segment to both those lines. Geometry part is now over. Now we enter into the purely algebraic part of how to do this. Well, let's kind of break this down in kind of a planning step first to understand what we need to do. So you were asked to find distance. Okay, that's fine. I want to find distance. Well, what are ways that we actually have to find a distance between anything? Well, hopefully you guys have thought about that. Pause the video if you have not, and realize that the only thing we have is a distance formula. Okay, fantastic. We have the distance formula. Well, okay, what do I need to operate the distance formula? Well, if you think about how it's written, if not, go look it up. The only inputs possible are two coordinate pairs. I should say one pair of points. My English teacher is not happy with me. One pair of points. In other words, I need a coordinate. So I need like an x1, y1, and an x2, y2. That's the only way I can actually operate the distance formula. So how do I actually get one pair of points, 2 points, one in either end of this segment I'm talking about? Well, if I know the definition of parallel lines, I know that the distance I'm looking for can actually occur anywhere on these lines. So what I'm going to do is actually pick them really, really carefully. So let me extend this to kind of emphasize what I mean. I could pick it here, where this line I'm looking for goes through the origin, which I saw some people do, which seems clever superficially, but let me tell you how crazy silly this idea is. So you're telling me to use a distance formula, I need to have a pair of points, one in each end. So if I position my perpendicular line here, that means I need to find this coordinate point and this coordinate point. Now, if you don't know why that's silly and ridiculous, look very carefully. What is the coordinate of this? Not guessing, what's the precise coordinate of this intersection? How about this one? So that means you're going to have to find two separate intersections before you can even use a distance formula. That's bananas. I would not do that, especially since I know I can place this absolutely anywhere on this grid. So why not kind of search for a better starting point or a better kind of placement point? Here isn't bad. Look at that guy. That'd be pretty good because, I mean, we can definitely tell where this point is. Okay. We don't know where this one is, which means we're going to have to find it, but we can actually at least find this one automatically. I personally would not use this one, though. And I'm going to explain kind of moving forward why I would not use this one, why, in fact, I'd actually use this guy. But to understand why I would make this choice, you have to understand how we're going to actually end up with the second coordinate. This guy is totally cool. I'm going to call this coordinate A. I'm not even going to write the numbers to it. It's going to be 0, 3. The reason why I want to pick it here is because of how I need to find the point here. Thinking back to Algebra 1, if you want to find a specific location on a grid, especially that occurs lines, that is paramount to actually finding the intersection of two lines. So to find coordinate B, I'm going to have to find the intersection of line Q and line M. That's the only way I'm going to be able to do it. So I'm picking this point because to find the intersection, to find the points, that means I'm going to need the equations of both line Q and line M. That's really where this algebraic problem starts, to find the equation, which is also why we said in class that you had to come in knowing how to write lines or linear equations, especially linear equations that are parallel or perpendicular to other lines. If you didn't come in with that knowledge, you probably walked out today extremely, extremely confused because you got so bogged down in the algebra that there's no possible way out of it. Okay? We expect you guys to be very good algebraically. If not, we expect you to get the help you need or find the help you need or find the information somewhere, doesn't matter where, but this is something you absolutely have to be able to do. In fact, I'm not talking about how to do this in this video. That's a whole other kind of ball of wax. That was a separate videos, or actually separate videos I posted, or ones you can easily find on YouTube. So that's where this starts. So let's find the equation, or let's write the equation, I should say, very quickly for line Q and line M. So line Q, I'm looking at y equals, let's see, 1, 2, 3 over 1. So y equals negative 3x minus 5. And for line M, I'm choosing, let's see, because it's perpendicular, it's got to be 1 over 3x plus 3, which also kind of tells you why I chose this point. Is because I want to write this equation efficiently using point-slope form and not, slope-intercept form and not point-slope form. So now that we found the equation, we have to find the intersection to find the other point to help us use a distance formula to find the distance. In other words, we have to find this intersection, the happy intersection. Why is it happy? Because I made it so. Bam, happy intersection. Now to do this work going forward, I'm going to go ahead and take off this grid, just because I don't want all this grid to kind of get in our way. But we should kind of look ahead of time. This point we end up with for B should be around negative 2-ish and around positive 2-ish for our values. So that's something we got to keep in mind. So goodbye grid. Right. So to find B, let's jump into the algebra, because from here on out, it is purely algebraic work. This is straight up Algebra 1. No kidding. You should be able to do this kind of Algebra 1 work. Like, don't disappoint Mrs. Fike. She wouldn't like it. So let's go ahead and annotate what we're doing. So we're going to, in this next section, to find the coordinates of B. We're going to find the coordinates of B by finding this intersection. So let's do it. To find the intersection of two lines, y equals negative 3x minus 5, and y equals 1/3 x plus 3, we have to think back to your Algebra 1 days. This is all about a system of linear equations, meaning that you can solve the intersection by graphing. If you have a graphing calculator, it's much faster. You can look for the values are shared in the table. You can also use linear combinations, also called elimination or even substitution. Point being, we have to find the x and y values that exist on both lines, hence solving these equations as a system. For the purposes of what I want to do, I'm going to go ahead and use a graphing calculator, because I think that's the fastest way to do it, and why wouldn't I use the tools and technology I have at my disposal? If you want to kind of discuss the more algebraic ways to do it, I will totally entertain that conversation, but let's entertain that conversation at a different time. Hey, calculator, turn on. Okay, so I'm looking for the intersection of these two lines, so let's type it in. Y equals 3x minus 5. Bam. And the next one is going to be negative 1/3. So I'm going to negative, in parentheses, 1 divided by 3. You've got to be creative using a graphing calculator. Plus 3. So I'm going to check the graph against what I have to see if that's kind of accurate to what I'm looking at. Oh, you guys see my mistake? I bet you guys caught it already. That should be positive 1/3. How come you guys didn't say anything while I was making this video here by myself? Okay, so that kind of looks legit. I mean, we can even put in the equation of the other line if we want, but I don't think we need it. I'm looking for this intersection, bam, right there. Now, to do that, the quickest way, hit your second key to access your calculate menu. Drop it down here to intersect, boom. First curve means is this the first equation, y equals negative 3x minus 5? It is. I'll hit enter to confirm. Second curve, is this the second equation? It is indeed. Guess, I'm not going to do that because it's only one possible intersection. Bam, hit it. Intersection is negative 2.4 and then positive 2.2. So let me go ahead and record that. In fact, that was pretty close to our original estimation. If you don't believe me, back up that video and check it out. So negative 2.4 comma 2.2. Okay. In fact, let's go ahead and back this away. We're going to come back to that calculator. We're going to use that thing. But if I bring back the grid, okay, we can see that negative 2.4 and positive 2.2 is a very reasonable estimate, so we can have high confidence that this is actually the answer. So we've now found both pairs of points. Man, that's messy. Let me see if I can fix that. Bam, bam, bam. Okay. So negative 2.2 and then positive 2.4. Methinks. Let me double check. Oh, got him switched around. Again, how come nobody told me? Just kidding, you guys aren't here. So I erased them so they're less messy, and I made them more messy in the process. Ain't that grand? Okay, so anyway, we've now found our second pair of points. Now this problem is completely reduced to just using the distance formula. If I want the distance between these lines, all you have to do now is use a distance formula to find them. So again, we don't need these anymore. These are not useful. Let's get rid of those. In fact, let's get rid of those. Let's get rid of that. Don't need that either. Don't need that either. Okay, so now we need the distance formula between these 2 points. We're calling the distance formula, and I'm going to use the distance formula now in its full form, where the distance is going to be equal to the change in x, defined to be by x, the first x value, subtract off the second x value, squared, and then the distance of difference in y's, which would be y1 minus y2, squared. Of course, this is a Pythagorean theorem, just kind of played out in a different algebraic sense. So x1 minus x2, I'll choose A to be my x1 point. So that's 0, subtract off 2.4. I do not like that. And add that to y1 minus y2. Since I've already established A as my 1 point, that should be 3, subtract off 2.2. And squared. Okay. So if you're wondering why that became a positive, consider that 2 negatives make a positive, and that's already negative. Okay, so finding my distance, I'm going to come back to Mr. Calculator. So I have 0, add 2.4 squared, and add 3 minus 2.2 squared. Okay, so I'm looking at the square root of 3.6864, which seems oddly specific. And then we're going to now take the square root of this guy, which means the distance between these lines is approximately 1.92. Okay, so again, to kind of review the steps that we took, the first, to find the distance, we need a distance formula. To do that, we need a pair of points, which means we need an intersection of lines that are perpendicular, which means we have to start with the equations. So in the end, this problem is reduced really to a big algebra problem. The geometric part is knowing that the position has to be perpendicular, and then intelligently picking where those points have to be. Beyond that, that's what we have. So I hope this helps you guys. This is literally the same way it would work pretty much every single problem on this page, with the exception of the first one, of course. So if there's any questions, please post them below. Again, we are expecting you to be able to do this right now, like today, right now, no kidding. Walking tomorrow, we expect you guys to be able to find the distance between two parallel lines on a grid. So review this, practice it, work it. Tomorrow we're going to have keys in class. Other than that, thank you for watching. Spread the word. Have a great night.